started. I'll give you extra credit though. All right. All righty. Today we are talking about posthoc tests. I have teased the posthoc test for a while now. Why do we even need to run a posthoc test?
Because you said like the tests we've been doing will only show that there's a difference, not where the difference is coming from.
Exactly. Good job, Sonny. Yeah. So ANOVAs are only going to tell you that there is a difference. It doesn't tell you where the difference exists. So if I have 3 groups and my test is only telling me that there is a difference, but not where that difference lies, that's insufficient, right? I'll come back to this in just a second. Why is this not working? All right. So, yeah, if you have 3 conditions, and ANOVA is just going to tell you that there is a difference between these groups somehow. It doesn't tell you where that difference exists. It doesn't tell you really anything meaningful about this, right? What you want to know is, okay, there is a significant difference between these conditions, but what's larger than what? What's smaller than what? Where's that difference lie, right? So maybe condition 1 is significantly higher than 2 and 3. Maybe it's higher than 2, lower than 3. No, that was from before. Thank you. Appreciate it. No, you're fine. I appreciate you letting me know. So a posthoc test is going to allow you to establish where differences exist when you've run an ANOVA. So what did we learn last time before we actually get into the posthoc tests?
How you can use like a 2-factor or a factorial ANOVA to see about, like, to measure interactions.
Exactly. So what is a 2-factor ANOVA?
It's a statistic test when you have 2 independent variables.
Yes, 2 independent variables. Exactly. So can you give me an example of what that type of test would look like, Caleb?
I guess kind of like if you're doing, let's see, if you're doing, what was it, rainy or sunny and cold versus warm, but you're like consolidating all those together. Yeah. Weather.
Right. And so let's say we've got one independent variable of weather, so rainy versus clear, and temperature, cold versus warm. And I want to see how much people pay attention in class, right? So the weather may have an effect. The temperature in the classroom may have an effect, or there may be an interaction between those, right? So when we run a repeated measures ANOVA, we get a main effect evaluation for weather, we get a main effect evaluation for temperature, and then we get the interaction between the two. So maybe people don't pay attention when it's rainy, but they do when it's clear. Maybe they don't pay attention when it's warm in the classroom, but they do when it's cooler in the classroom. Or maybe they only don't pay attention when it's rainy and warm together. So that's the benefit of doing a factorial design or a 2-factor ANOVA. We get to start seeing a little bit more nuance in that data. Questions about what we covered last time? Cool. Cool, cool, cool. All right, so I've had conversations with a few folks over the last week or so about coming up for this exam and what to do for this class. You know, for a lot of other classes in these sort of soft sciences, the classes that are not math-based usually can get away with doing flashcards and various studying habits. But your best bet when it comes to studying for the exams in stats or any math-based class is a crap ton of practice, right? Practice, practice, practice. Do it until you don't have any questions or any apprehensions about how to actually do the problems, right? And so I post the practice problems. Make sure you're doing those practice problems. And in fact, those practice problems are usually going to be your best bet for if you are stuck and don't know how to do the problem, because I'm walking you through step by step. But good news about stats is it's taught pretty much at every university across the world, right? And so there are a lot of practice problems out there on the interwebs that you can do. There are practice problems in the back of your book. If you decided to get the mind tap, there are practice problems on there. And if you are so inclined, you can create your own data, do the practice problem, and then test your answer with SPSS as y'all are doing for lab. So now is the right time to have started practicing for the next exam, although you should have done so before. All right, here is your fun fact of the day. Dorset, Minnesota picks a new mayor every 2 years by drawing names out of a hat. In 2015, the new mayor was a 3-year-old named Robert Tufts. I don't know who had to change the mayor's diaper, but I think it's very funny that that would have had to happen. I think he got the same mayor. I kind of like that. Maybe we should do that for like presidential politics. I think it'd be less vitriolic. Just pick random people. All right, so today we're talking about those post hoc tests, post tests, right? So post hoc is just Latin for after the fact, right? You may have heard post hoc, ergo propter hoc, after, therefore, because of. Post hoc just means after. And these comparisons are going to let you go back through the data and compare treatments 2 at a time. All right, so again, if we have 3 conditions, you know that there may be a difference between these, but now I want to see where the difference lies. So I'm going to compare condition 1 to condition 2, why do I keep saying condition? Condition 1 to condition 3, and condition 2 to condition 3. And so I'm going to go over 2 different types of tests today. Tukey's HSD, and I looked this up. It's not Scheffe, it's not Scheffe's, Scheffe's test. There we go. And for each one of them, we're going to have our alpha level, right? And the tests are going to be done a little bit differently. But again, you're going to have to know the alpha level at which you are interested in testing at. All right, and so let's just pretend that we have these 3 different conditions. We've got T for each one of them. And what is T again? The total. Yep, exactly. The total for the column. We have our sum of squares. We have our n, or little n, which is the number of data points for each one of these columns. And then we're going back to the means here. Right? So when you see m, that is the mean. And then the rest of the stuff, what is k?
Number of categories.
Yeah, number of categories, conditions, exactly. In this case, we have 3, 15 observations. G, that grand total, which is all of the data points added together. And the sum of x squared is every data point squared added together. So we have all of that. This is where we're going to be pulling from for the practice examples today. After you do all that, you should get a source table, right? And that source table is going to give you the sum of squares, the degrees of freedom, that mean squares. And again, it's going to be a little bit of a review today, but how do you get mean squares?
Your sum of squares divided by your degrees of freedom.
Exactly. So sum of squares divided by degrees of freedom gives you your mean square. And is this a one-factor ANOVA, a repeated measures ANOVA, or a two-factor ANOVA?
So one factor.
How do you know?
Because because I only saw one row.
There's no SSA
Okay, yeah.
no between treatments or between subjects, right?
There's only one variable, right? Or just measure.
Yeah, so I'm sorry, I don't know who spoke up just a second ago, but whoever said that was absolutely right. Yeah, so you're missing a little bit of information that you would need for the repeated measures ANOVA, and you clearly don't have any interaction term nor main effects for certain variables. So, yes, this is a one-factor ANOVA. So, given that it's a one-factor ANOVA, how do you find the F ratio from this table?
Is it
And that's-
your?
Go ahead.
No, you're good.
It's the MS between over the MS within.
Exactly, yes. MS between divided by MS within gives you that F ratio. So again, if I were you, I would familiarize yourself with how everything relates to one another for the exam. All right, so the first one we're going over is Tukey's HSD. And it's a single value we're going to establish that determines the minimum difference between treatment means or treatment condition means to conclude that a difference is significant. And HSD stands for honestly significant difference. No, I'm not making that up. That's serious. So we will, before we run the Tukey's HSD, have run that omnibus ANOVA and shown that there was a significant difference between the conditions. It's typically the case, best practice, that you're not running post-hoc tests if the ANOVA itself wasn't significant. So to get that HSD value, we're going to take Q, which is going to be a value we look up in the back of the book, times the square root of the mean squares within divided by n. Now, one of the idiosyncrasies of Tukey's HSD is that that sample size has to be the same for all treatments. All right, so when I represent this with little n, that is not the total number of observations, that's the number in the condition, right? And so this number has to be the same for every group in order for us to use it. So once we find that HSD value, the difference between the means for the conditions of comparison has to be larger than that HSD value. So for Q, we're once again looking it up in the back of the book. And you're going to need two things. One, the number of treatments, or the number of conditions, so your K value. And then your degrees of freedom for the mean squares within. And how do you find the degrees of freedom for mean squares within again? What is that?
That's n minus k, right?
N minus K, yeah, big N minus K. So if we go back to our earlier example, we have K of 3, right? 3 conditions here. We have a big N of 15, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 minus 3 gives us 12. So we've got K of 3, degrees of freedom, mean squares within of 12. And then when we look it up in the back of the book, it's going to be a whole new table. And you'll see on the very top of that table, it will say K, or number of treatments. So that's where this number comes in. And then it will say the degrees of freedom for mean squares within on the left-hand side, and that's where this comes in. And just like with our F table, you go across the top row for the K number. You go down the degrees of freedom mean squares within. And then you again are going to get two numbers, right? So you'll get a number with light face and then a number with bold face, right? That light face one, I think is the 0.05. The bold face is the 0.01, but it says on top of your book. So when we do that, for 3 and 12, we get a Q value of 3.77, which we now have to plug into our equation. Question so far? Cool. All right, so we plug it in. So our Q value we know is 3.77. We're multiplying that by the square root of our mean squares within divided by n. And what's the equation to get the mean squares within?
The sum of squares within over the DEF, degrees of freedom within.
Mm-hmm. Right? And so in this case, you're taking sum of squares A plus sum of squares B plus sum of squares C over degrees of freedom A plus degrees of freedom B plus degrees of freedom C. And when you do that for our previous data, you get 1.33. So divide 1.33 by 5, take the square root of that, and then multiply that to our 3.77. And we get an HSD value of 1.94. So this is now the threshold by which we are making those pairwise comparisons. If the difference between two conditions is greater than 1.94, we say there's a significant difference between the two. If it's less than 1.94, we say there's no significant difference. So, again, we've got our HSD value here. These are the means for A, B, and C. So the mean for condition A was 1, the mean for condition B was 4, and the mean for condition C was 1 as well. And so now we can make comparisons, right? The absolute value of A mean minus B mean gives us 3. That is greater than that 1.94. So we say that there's a significant difference between A and B. I just did the absolute value. So it's the unsigned difference between the two of them. No, that's fine. Yeah, it's the unsigned difference. It's a good question. So don't worry about the directionality of which you're subtracting from which. Just take the absolute value of that difference. So it's a negative sign, just drop it. In this case only. We also know that there is a 3-unit difference between the mean of B and C. So there's a significant difference between that. And there's a 0-unit difference between A and C, so there's no significant difference there.
How does this help in the real world?
Yeah, so let's say who keeps calling me here. So let's say we are testing UAH. So let's do UAH, UAB, and UA Tuscaloosa on their, awesomeness scores, and lower is better in this case. We find that the awesomeness scores are different between these 3 groups when we actually run. Can you hear me now? Can you?
Yes.
Okay, cool. So we can tell that there is a significant difference when we run our ANOVA test, right? Because it'll give us some value, and then P is less than 0.05, but it doesn't say where that difference exists, right? And so it's pretty clear cut that if it's significantly different in this case, we know which one's larger and which ones are smaller. But let's say this was 1, this was 2.5, and that was 4. Now it becomes a little more muddied, right? So if there's a significant difference, we have to see, okay, well, in this case, UAH has a lower, which is better, awesomeness score than UAB, and that's significant. That 3-unit is significant when compared to 1.94. We're comparing 4 to 2.5. That gives us 1.5, so there's no significant difference between the groups in that case. And let's compare UAH to UA Tuscaloosa. That's, again, a 1.5 unit difference, so there's no significant difference again there. So the fact that we have a significant ANOVA in this case, right, if I were excluding that as 1 and making that 2.5, would be that there is only a difference between UAH and UAB, but nowhere else, right? So this significant main effect is driven only, at least primarily, by the difference between those 2 groups. Does that make sense?
That makes sense. Basically, if you just rely on the ANOVA, it could be too vague.
Yeah, so the ANOVA is just saying, is there a difference, right? The post-hoc test is saying, where does that difference lie?
All right, thank you.
Of course. It's a good question. All right, questions about Tukey's HSD? Cool. There's also a Tukey's LSD, but we never teach that, in part because I think students laugh all the time when we say LSD. Ah, good one. All right. So next, we're going over Scheffe's. Scheffe's post-hoc test, we can say, is the safest of all possible tests. And when we say safest, we essentially mean the most conservative, right? Remember when we talked about why we're even doing an ANOVA rather than a whole bunch of t-tests? Who remembers why we do that?
Because with t-tests, you can only do 2 at a time.
Well, yeah, so you can only do 2 at a time, but
Sorry.
It limits type 1 error.
yeah, exactly. So the biggest reason we do an ANOVA rather than a series of t-tests is that it limits that type 1 error rate, right? So we run a whole bunch of tests. If we've set our probability such that 1 in 20 of these tests are going to give us a false positive, if we run 20 tests, we're going to get a false positive, right? And so by running an ANOVA, that helps protect against this. Right? And so Scheffe's test is in the similar vein, the most kind of conservative, most protective against it. And so Scheffe's uses the F ratio to test the significance between any 2 treatments. And this F ratio is calculated with only the 2 treatments of interest, right? So again, you are running this after you run an omnibus ANOVA, right? Just the ANOVA itself. If it's significant, then you make these sort of pairwise comparisons with Scheffe's test. Is it a hand? Oh, no, just Sarah. So the denominator for Scheffe's is the same mean squares within that you will have used for the ANOVA initially. You are similarly going to be using K from the initial comparison, such that you have K minus 1 for the degrees of freedom between. And we're still using that F critical value, F crit, that we used for the main ANOVA, right? So when we found that F crit, we're using that same critical value threshold for the comparison. So let's say, I think this is the same data with just different labels.
We can't hear you if you're talking.
Just for good measure, Dr. T.
Dr. T, we can't actually hear you.
Oh no.
He just left us. He just left us.
At least we're in this together.
Yeah.
So how's everyone doing?
ANOVAs are fun. LOL. Ooh, who's doggy?
Even the dog gets it.
That's mine.
Aww.
You're on camera.
You're on camera.
Mine's asleep on our bed.
Oh,
Aww.
Doing dog show and tell, everybody.
yeah.
Who else has a dog? Panya's got a dog too.
Oh,
Oh,
there's
snap.
a dog's not allowed in my room.
Mine thinks she owns my room. So,
Mine's shedding like crazy right now. It's not okay.
oh, mine's super needy. Right there.
All right. Can you all hear me now?
Yeah, I can hear you.
Yeah.
Perfect. What was the last thing y'all heard?
The last slide.
Yeah, like
The
everything.
last slide.
Yeah.
So again, we're making the comparison between 50 and 70. And so we first need to calculate that sum of squares between, with the same equation we used before, but now we're only using two values, right? Two t's. And those two t's come from the variables of interest, right? And so if we were doing this for the full ANOVA, we would take every one of these t's, right? But because we're only comparing for Scheffe's test, the 50-degree condition and the 70-degree condition, those are the only two t's we're putting in there, right? So 5 squared divided by 5 plus 20 squared divided by 5, this got offset a little bit, minus that grand total. So we're still using the grand total from these two here, not all three of them, divided by n, right? So the n for these two groups. So again, once you're making this pairwise comparison, you're essentially just neglecting that third condition. And so if we were making a comparison between 50 and 90, that would be 5 squared divided by 5 plus 5 squared divided by 5 minus, adding those together, 10 squared divided by 10. But because we're doing the 50 and 70, we have these t's that we've used. We get 22.5. So we now have to calculate our new mean squares between. That mean squares between gives us a 22.5 divided by the degrees of freedom between. And again, we're using the k from the initial omnibus test. So 3 in this case. And once we do that, we then put it over our mean squares within. When we do that, in this case, we get 8.46. And we're still using our F critical that we would have used for the main ANOVA, right? So K minus 1 is that first degrees of freedom. N minus K is that second degrees of freedom. And so, based off of this new F test, do we say that there is a significant difference between the 50 and 70 degree conditions? I'll give you a hint. The answer is the last thing that was typed into the chat.
Okay, can you?
Yes.
Yes.
Yes, there you go. How'd you get it? Good for y'all. Caleb, you were starting to say something?
Yeah, okay. So the Scheffe test is I'm confused. So is it we're just taking our f value for each, if it's A or it's B, and then we're just using that and comparing it to the f critical value? Kind of confused.
Yes. So for every comparison, you are making your new sum of squares between, right? So you've already run your omnibus test where you had your sum of squares between, your sum of squares within, all of that good stuff. Now for the Scheffe's test, crap. For the Scheffe's test, you were calculating a new sum of squares between for only these variables of interest, right? And so for Scheffe's, if I want to compare 50 and 70, I'm just going to neglect 90, right? So now I calculate a new sum of squares between for 50 and 70 using the equations we've used before, like we have here. That gives us the sum of squares between. We have to get that mean squares between. So we've got our sum of squares between. The degrees of freedom between stays the same as it was in the omnibus test, which gives us that mean squares between. And now we get a new f value, which we compare to our original f critical value, right? So this is the f critical value we would have used for the main ANOVA test. But we have our new f value that we're comparing against that f critical. And so in this case, we are rejecting the null, and we are saying that there is a significant difference between the 50-degree condition and the 70-degree condition, because that f value that we got here is greater than this f critical value.
Got it. Thank you.
So, yep, Amber says, so we were just doing the problem over again with only 2 of them instead of all 3, and then have to do that like 3 times for this problem. Sort of. So you're not doing the whole problem over again, right? Some of that information is carrying over, right? The mean squares within is the same as you used before. So you don't have to calculate the whole thing. You just have to calculate a new sum of squares between for each of those pairs. So yes, you were doing it 3 times for this problem.
Do you have to calculate a new mean squares within? I'm sorry. I
Nope,
didn't
you're
get
using
that.
the same mean squares within that you calculated for the ANOVA. So once you calculate that for the main ANOVA, you just get to carry that one over.
Okay, and also, did you say that you're rejecting the null hypothesis because, 3.8 is smaller than 8.46?
Exactly, yes. So the null hypothesis in this case would be that there's no difference between 50 and 70, but our results indicate that that's not true, so we reject the null. Does that make sense?
Yeah, thank you.
Mm-hmm. What other questions do we have?
So the other way to do it, the Tukey's HSD is a quicker way to do it, but it's not as secure.
Exactly. Yep. Yeah, there are multiple ways to skin a cat, and once you go, if y'all go into academia, one of the things you'll notice is everybody has a strong held preference with enough justification to convince you, but there's not necessarily a right answer. AKA all academicians are bloviating windbags who want you to think that they're the smartest person in the room, and so they'll tell you one's better than the other. Doesn't necessarily make it true. Other questions?
So
All
in the
right.
exam,
So we are.
if
ahead.
we did this, would we have to write out the null hypothesis as well? for each and every one of them?
For if I say explicitly, then yes. Otherwise, don't worry about it.
Okay, thank
Mm-hmm. All right, so we're going to end a little bit early today. I will hang out if people have questions. Yes, good point, Caleb. I will hang out if people have questions. I'm more than happy to answer them about these post hocs or about ANOVAs. Next time we are moving on to regressions. Regressions are where things get exciting, right? Regressions allow for prediction. Regressions are what allow us to establish essentially the foundation for what is machine learning, for artificial intelligence, stuff like that. So that gets exciting. Again, I will hang out here until all questions have been answered. Otherwise, have a great weekend. Hopefully it doesn't rain as much. And I will see you all on Monday.
Are you gonna post practice problems for this stuff too?
I will.
Yeah.
Could you please go over the Tukey's test? It was quite long, and I got lost in some parts.
Okay.
Can I
So
ask you a
for
question before you
Tukey's-
do the whole problem?
Sure.
So on that, it's what, DF MSW? Why is it not just the DF like within? Why does it have to be I mean, they're the same thing, right?
What are you talking about? You're talking about
Like you had
for
DF MSW. Oh, for Tukey's. That's what she was talking about, right?
Yeah. Well,
gotcha.
You need the
Gotcha.
DF and the K
Um,
just to find the MS, right?
Yeah,
Is
so
it
yeah, it's just a DF. It's degrees of freedom for what you would have gotten for that mean squares within. So that would just be the degrees of freedom within.
Okay, I was just like, is there a whole other step that I'm missing? Okay.
Nope, it's just big N minus K.
Okay.
Cool.
Yes.
Yeah.
All right. All right. So going over Tukey's HSD again. The equation for Tukey's HSD is Q, and Q is going to be a number we're looking up in the back of the book, times the square root of the mean squares within that we calculated for the problem, divided by the number of people in each condition.
Mhm.
So for that Q, you'll see in the back of the book, you need two different numbers. You need the number of treatments, aka K. So in this case, the number of treatments would be, how many, Sonny?
3.
Exactly. Yep. So it would be 3. And then you need the degrees of freedom for within, which again is big N minus K. So big N is 15, right? You have 15 data points. So that gives you 12. So in this case, K equals 3. Degrees of freedom within equals 12. Got that down there. So when you look that up in the back of the book,
Sorry, is this degrees of freedom MSW or just within?
same thing, just within.
Okay.
That makes sense? Yep. All right. So once you look that up in the back of the book, you get that 3.77 for Q, and then you just plug that in, all right? So HSD equals the Q times that square root of the mean squares within divided by lowercase n. And so you get that 3.77 that we looked up in the back of the book times the square root of the mean squares within, which is the mean squares within for this data, as we got here, 1.33, divided by 5, which is the number of participants in each condition here. So 1, 2, 3, 4, 5. So this has to be that every condition has the exact same number of participants. It's just one of the idiosyncrasies about this type of test. And when we do that, we get 3.77 times whatever this simplifies down to, the square root of that, or an HSD of 1.94. So this is our critical value now that we're going to compare the mean differences against. So we have our HSD of 1.94. The difference between 1 and 4 is 3, because 3 is greater than this critical value here. That means there is a significant difference between A and B. Let's just continue on with the new data I have here, rather 2.5. We would say that there is a 1.5 difference in means between A and C. Compare that against our 1.94. That's not bigger than 1.94. And so we say that there is no significant difference between A and C.
Wait, because 2.5 is because I'm sorry, what number did you compare 2.5 or 2.5 subtracted from 1 or something like that?
Yeah, so it's the mean difference, right? And so it would be the difference between 1 and 2.5 here. So the difference between 1 and 2.5 is just 1.5. Right? So that would be the mean difference for A and C. Right? Because that number is less than that 1.94. We retain the null hypothesis, and so we say that A is not different than C. We now have to do that for B. So B, we have 4. C, we have 2.5. The mean difference between 4 and 2.5, again, gives us 1.5, which we know is not significantly different from that 1.94, which means we, again, retain the null hypothesis. So with this new data I have here, so I'm excluding, that's no longer 1, that's 2.5. What I'm saying is that the only difference, significant difference, which exists in the pairs is the difference between A and B.
Okay.
A is significantly smaller than B, but there is no statistical difference between A and C, nor B and C. Does that make sense?
Yes, that does. Could you
Awesome.
please go out to check the book? Like, so you said you so does that mean like you check for 3 in the numerator part and then 12 in the denominator part? Like, is that how you check it? That part always confuses me.
Yes. Yeah, so for the back of the book here, you need, again, that K, that 12. So yeah, you are looking in the back of the book. Atop that back of the book, you're going to have, it's going to say, you're going to essentially have 2 columns here. This is going to be the K values. This is going to be the degrees of freedom within. And so you find 3 up here, you find 12 down here, and you find that intersection point. And where they intersect, that gives you that value.
Okay. Thank you.
Of course. It's Appendix B. It comes after the F table. I don't remember what page it's on, but you'll see it. It says like Q statistic table or something like that. What other questions do we have about post-hoc tests? All right. Well, if there's nothing else.
Can I ask you a question about the ANOVA stuff?
Sure. Yeah, absolutely.
Okay, for some reason, I cannot tell you why, but I've done like 2 or 3 practice problems And the
Mhm.
SSA and SSB where you do the T things, I know I got you to explain it to me last time, but it's like, you just get the totals of everything and square them and divide them by the little n and then subtract it from g squared over n. But like, I keep getting weird numbers. I don't know what I'm doing wrong.
So I'm happy to go over it. If you keep getting weird numbers, maybe it's best for us to set up a meeting just so I can look at what your actual math is to see where you're going wrong. But yes, let me pull that up real quick here.
Are you talking about for two-factor, Amber?
Yeah. Dude, I know we've been going over it, but it's just like, it's not working out for me.
Where are you going wrong? Is it?
Don't worry about it.
I have no idea.
All right. So when you're looking for factor A, right? So you're looking, is there a main difference between factor A? This is your new total. Total 1, total 2. Right? So when we, where is it? Here, when we're using this equation for sum of squares A, it's total 1 for A squared divided by n of A, plus total 2 squared of A divided by n of A. So in this case, it would be 90 squared. Is that a victory stretch or what's happening?
Yeah, no, I got it. Because I've been just squaring the
Okay.
numbers, the t's inside, like 25, 45, and 20.
Nope.
Yep. And then adding them together. And then, okay. So then it'd be
Perfect.
90 squared over 15?
15. Yep.
Okay.
Plus
Simple
30
enough.
squared divided by 15 down here. Yep.
Awesome.
And then for B, you're just doing 30 squared divided by 10 plus 50 squared divided by 10 plus 40 squared divided by 10.
Okay, thank you.
Capiche?
Yeah.
Of course. All right. Well, if y'all want to set up meetings to go over anything else, let me know. I will post a practice problem this afternoon for Tukeys and Scheffes, and have fun running those. And I will see you all after the weekend. Have a good Halloween, a safe Halloween.
Yeah. Can I talk to you once everyone's gone?
Yeah, absolutely.
It's not a math problem.
Yeah. All right. See you all Monday.